In 1956, a Swedish engineer walked into a meeting with his country's military leadership and proposed building a tank without a turret. The reaction in the room was immediate and uniform. Generals laughed. Technical experts shook their heads. Foreign observers who heard about the proposal called it an engineering absurdity. A tank without a turret was not a tank. It was a self-propelled gun, a vehicle category that the military world had already defined, already understood, and already considered categorically inferior to a proper main battle tank with a rotating gun mount that could engage targets in any direction without moving the vehicle. The engineer's name was Sven Berger, and he was 40 years old, and he was not laughing. 10 years after that meeting, the vehicle he had proposed was in service with the Swedish Army. 20 years after that meeting, British and American tank crews had evaluated it and written reports calling it revolutionary. 30 years after that meeting, it fought a final engagement against its own replacement, a modern German tank widely considered among the best in the world, and won decisively. And then it was retired, not because it had failed, but because the world it had been designed for had changed. This is the story of how one engineer convinced an entire country to build something that violated every established principle of tank design, and why the result turned out to be right in ways that nobody, including the engineer himself, had fully anticipated. To understand why Berger's idea landed the way it did, you have to understand the situation Sweden found itself in during the early 1950s. The country was neutral, committed by policy and by national identity to remaining outside the military alliances that divided Europe into opposing armed camps. But neutrality did not mean vulnerability was acceptable, and the military geography of Sweden's situation made the potential threat very clear.
The Soviet Union, with its vast armored forces and its demonstrated willingness to use military power to secure its peripheral interests, was a presence that Swedish defense planners could not ignore, regardless of what their country's formal diplomatic posture required. The Swedish Army's tank inventory at the time was built around British heavy tanks, large, capable vehicles by the standards of their era, but designed for a different kind of warfare in a different kind of terrain. Sweden is not the North German plain. Sweden is forests, lakes, rivers, ridgelines, and the specific tactical geography of a country where the defensive advantages of terrain are available to any force that knows how to use them. The heavy British tanks were slow, tall, heavy, and difficult to conceal. They were the wrong tool for the environment. A domestic tank development program had been running since the late 1940s, under a series of designations, aimed at producing a vehicle optimized for Swedish conditions, lighter than the British tanks, more mobile, better suited to the terrain. The program had been ambitious, the technical requirements demanding, and the cost unsustainable. When Britain offered to sell additional heavy tanks at terms that made the domestic program look economically indefensible, the official work largely stopped. But the underlying need had not been met. The officers who had thought seriously about what Sweden actually needed in a tank continued to think about it, and Berger was one of them. He had qualifications that were unusual for someone working in a procurement and inspection role. He was a reserve officer who had commanded tanks in training, which meant his understanding of the vehicle's limitations was not theoretical but experiential. He had sat inside one, operated the controls, tried to see through the vision equipment, tried to identify and engage targets under the pressure of an exercise, and formed opinions about what worked and what didn't that could not have been developed from technical documents alone. He also read widely and in multiple languages, which gave him access to technical literature and after-action analyses from countries whose military establishments
published primarily in languages other than Swedish, including the countries whose tanks Sweden might actually have to fight. What he read, and what led directly to his proposal, was the statistical record of tank losses in the two most recent large-scale armored conflicts, the Second World War and the Korean War. The data, when analyzed carefully, told a story that was both clear and disturbing. The height of a tank, its vertical profile, the distance from the ground to the highest point of the vehicle, was directly correlated with its probability of being hit and destroyed in combat. Taller tanks were hit more often, and when the data was broken down further by which part of the tank had been penetrated in fatal engagements, the turret emerged as the most common answer by a substantial margin. The turret was the highest part of the tank. It was also the part that had to be exposed to aim and fire the gun. The combination of height and necessity of exposure made it the most vulnerable component of the vehicle, and more than half of the fatal tank losses in the datasets Berger analyzed had resulted from turret penetrations.
The logical conclusion, stated simply, a tank without a turret would be shorter, and a shorter tank would be harder to hit. And a tank that was harder to hit would have better survival rates in combat than a taller tank with equivalent armor protection. The turret was not just the source of the vulnerability. It was a large, mechanically complex, heavy, expensive component whose removal would simplify the vehicle, reduce its cost, and make room for other improvements. The problem, obvious to anyone who thought about it for 30 seconds, was how you aimed the gun without a turret. A rotating turret exists precisely to allow the gun to be directed at targets in any direction without moving the entire vehicle. Remove the turret and fix the gun to the hull, and you lose the ability to engage targets without pointing the tank at them. To point the tank at a target horizontally, you have to drive the tank. You have to use the tracks and the transmission to rotate the vehicle on its axis, which takes longer than traversing a turret and requires a surface suitable for vehicle movement. To change the elevation of the gun vertically, you have to somehow change the angle of the vehicle itself, which normally requires a hill or a depression in the terrain. Berger's solution to both problems was the one that made his patent application distinctive, and that his engineering analysis suggested was actually achievable with available technology. For horizontal aiming, the tank would use its own transmission, a highly precise automatic transmission that could rotate the vehicle in small, controlled increments with sufficient accuracy for fire control purposes. For vertical aiming, the tank would use a hydraulic suspension system that could raise and lower the vehicle's front relative to its rear, effectively tilting the entire hull forward or backward to elevate or depress the gun. Both of these solutions required technology that was either at the frontier of what was available or slightly beyond it. Precise automatic transmissions capable of fine vehicle rotation for fire control were not standard military hardware. Hydraulic suspension systems capable of the kind of controlled articulation that vertical gun aiming required did not exist in production form. But Berger's engineering analysis suggested that neither was beyond the reach of Swedish industry, and the potential payoff, a tank that was dramatically lower than any conventional design, potentially cheaper because of the eliminated turret, and optimized for exactly the kind of defensive ambush combat that Swedish terrain supported, justified the development risk. When he presented the concept to his superiors in the summer of 1956, the reception was, as noted, skeptical. But it was not dismissive enough to close the door entirely. The military establishment understood that if the concept worked, Sweden would have something that no other country had: a production tank designed from first principles around the specific requirements of the Swedish operational environment, rather than adapted from designs created for someone else's war. In a country whose entire defense posture
rested on the principle of self-reliance and the demonstration that its neutrality was backed by genuine capability, the national prestige argument had real weight alongside the operational one. Work continued. The early phase focused on proving that the core technical claims were achievable, that a hull-mounted gun could be aimed with sufficient precision using vehicle movement and suspension articulation to actually hit targets in combat. A test rig was constructed using components from available vehicles, fitted with the experimental hydraulic suspension system that Berger's concept required. The system worked. The hull could be tilted with the precision that fire control required.
The transmission could rotate the vehicle with enough accuracy for horizontal targeting. The conceptual objection that had caused the generals to laugh, "You cannot aim a gun without a turret," turned out to be answerable with existing engineering principles, applied in an unconventional way. By 1957, the program had been formalized into a competitive evaluation alongside two more conventional design concepts. The conventional approaches followed established European design schools, one heavier and more heavily armored, one lighter and faster, both with rotating turrets and conventional fire control systems. The unconventional approach, Berger's concept, was designated with a letter representing Sweden itself. All three were to be evaluated against the same tactical requirements with the same armament, so that the fundamental question of turret versus no turret could be assessed independently of the other variables. The comparison was structured to be fair, but the unconventional design faced an inherent disadvantage that no amount of analytical rigor could entirely eliminate. It required technology that did not yet exist in proven form, while the conventional designs could draw on decades of established practice. The hydropneumatic suspension that vertical gun aiming required had to be developed. The automatic transmission that horizontal aiming required had to be developed. The fire control integration that made both systems work together in combat conditions had to be developed. Each of these development challenges carried risk that the conventional alternatives did not face. The parliamentary debate that decided which approach Sweden would pursue was unusual for a weapons procurement decision, genuinely contentious, with serious technical and strategic arguments on multiple sides. The conventional designs had advocates who pointed to proven principles and manageable risk. The unconventional design had Berger, who had spent years developing the statistical and engineering case for his approach, and who argued with the particular conviction of someone who had derived his conclusions from evidence rather than adopted them from authority. The decision that came out of that debate surprised nearly everyone involved. Sweden chose the unconventional design. Not primarily because the engineering arguments were conclusive, the engineering was still unproven at that point, but because building something entirely new, something that no other country had attempted, was itself a statement about Swedish industrial capability and national self-sufficiency that the parliamentary consensus found compelling. A neutral country that could design and produce a genuinely novel weapon system was making a different kind of argument about its security than one that could only purchase other people's designs. The development that followed was genuinely challenging and genuinely innovative in ways that went beyond what even Berger had proposed in his original concept. The propulsion system that emerged was unlike anything in production anywhere in the world. Two entirely different engines, a diesel for ordinary movement and a gas turbine for situations requiring maximum power, operated together in a combined system that could draw on either or both, depending on the tactical requirement. The diesel provided the fuel efficiency needed for sustained operations. The turbine provided the power density needed for the rapid acceleration and high-speed maneuver that the vehicle's tactical role in Swedish terrain demanded. No production tank anywhere in the world had incorporated a gas turbine into its powertrain at the time this decision was made.
The technology existed in aviation. It existed in some experimental and prototype applications, but a tank that routinely operated with a turbine as part of its standard propulsion system was an engineering first, and the development challenges that came with it were real. The turbine selected for the initial production vehicles turned out to be significantly underpowered for the vehicle's weight, producing performance figures well below what the design had specified. The problem required a more powerful turbine replacement that added to the development cost and delayed full operational capability. The gun that went into the vehicle was a British design, a 105mm weapon that had been selected across several NATO armies as a standard tank armament, and whose ammunition was available from multiple sources. Fitting it to a turretless hull required solving integration problems that no previous designer had faced. The gun passed through the front of the vehicle and extended well beyond the hull front, with the breech mechanism inside and the barrel projecting in a way that looked, from outside the vehicle, dramatically different from any conventional tank. The empty cartridge cases were automatically extracted and ejected through an opening in the rear of the vehicle, a system that kept the crew compartment clear of hot brass during sustained fire and that required careful engineering to function reliably. The automatic loading system connected to this gun gave the vehicle a rate of fire that manual loading could not match. A trained human loader in a conventional tank can manage somewhere between 8 and 12 rounds per minute under ideal conditions. The automatic system in the turretless vehicle could sustain 15 rounds per minute, a round every 4 seconds, without tiring, without losing concentration, and without the performance degradation that human loaders experience as physical fatigue accumulates during extended combat. This rate of fire advantage was directly related to the decision to eliminate the turret. In a conventional tank, the human loader is necessary partly because the gun's position in the rotating turret makes mechanical loading systems complicated and expensive. Fix the gun to the hull, and the engineering of an automatic loader becomes substantially simpler, because the spatial relationship between the ammunition storage and the gun breech is fixed and predictable, rather than varying with turret rotation. Berger had recognized this secondary benefit early in his design process, and it proved to be one of the vehicle's most significant operational advantages. The crew arrangement that the turretless design required was unusual and took some time to stabilize. The original concept had suggested that the fixed gun and automatic loader could reduce the crew to 2 people, eliminating the loader entirely. Practical experience during the evaluation phase revealed that 2 crew members were insufficient, not for operating the vehicle and firing the gun, which could indeed be managed by 2 people, but for all the other tasks that a combat vehicle's crew must perform: maintenance, surveillance, communication, ammunition replenishment, and the basic physical security of the vehicle when it was stationary. 3 crew members were ultimately specified. The arrangement of those 3 crew members produced one of the vehicle's most distinctive features. The driver, who controlled the vehicle during forward movement, sat in the normal position, oriented toward the front. But a second driver sat in the rear of the vehicle, facing backward. This rear-facing driver had a complete set of driving controls, identical in function to the forward driver's position, and could take control of the vehicle when it needed to move in reverse. The tactical reason for this arrangement was central to the vehicle's entire operating concept. A tank engaging a target from a hull-down position, the vehicle's hull concealed behind a ridgeline or earthwork with only the gun barrel exposed to fire, needs to be able to return to full concealment quickly after firing. In a conventional tank, this means reversing, moving backward, which in most vehicles is slower and less controllable than forward movement. In the turretless vehicle, reversing was literally equivalent to the rear driver driving forward from his position. The vehicle could move backward at its full operational speed with the same control and precision as forward movement, allowing it to expose itself for a shot and then disappear behind cover faster than any conventional tank could manage the same maneuver. This capability was not just a tactical nicety, it was fundamental to the combat philosophy that the vehicle embodied. The concept of operation was not to find the enemy, close with him, and defeat him in an exchange of fire at close range. The concept was to occupy a prepared position with excellent concealment, identify the enemy at the maximum range where the automatic fire control could guarantee a first-round hit, fire 1 or 2 rounds from concealment, and then withdraw at speed before the enemy could locate and engage the firing position. The low profile made the vehicle difficult to detect. The automatic loader made each exposure from cover more lethal. The rear driver made the return to cover faster. Every element of the design worked together toward this single tactical vision. The armor protection philosophy reflected the same logic. The hull was narrow and low, with frontal plates angled at an extreme rake from the vertical, so extreme that the physical thickness of the plate, which was modest by the standards of the era, translated into an effective protection level that was substantially greater than the plate thickness alone would suggest.
A projectile striking an angled surface at a shallow angle is not punching straight through the armor's nominal thickness. It is traveling through a much longer path of material, encountering much greater resistance, and is also subject to deflection forces that can cause it to ricochet rather than penetrate. The frontal protection of the vehicle, tested against the ammunition threats current at the time of its introduction, proved to be considerably better than initial skeptics had predicted, despite the comparatively thin physical plate. A supplementary protection system was developed and held in strict secrecy throughout most of the vehicle's service life. A steel mesh structure, spaced some distance from the hull's actual surface, was designed to be mounted on the vehicle's front in the event of actual war. The function of this screen was to initiate the detonation of shape-charge warheads, the type used in rocket-propelled grenades and anti-tank guided missiles, at a distance from the vehicle's actual armor, rather than at the point of contact. A shaped charge detonated prematurely loses much of its penetrating effect as the focus jet of metal and gas that the warhead produces disperses over the distance between the screen and the hull. The same charge that would have penetrated the hull's armor if it had detonated on contact might fail to penetrate it after traveling through even a meter of air following premature detonation. The fact that this protection system was held in reserve and kept secret is itself operationally significant. Swedish doctrine held that revealing the vehicle's full capability in peacetime would allow potential adversaries to develop countermeasures. The screen would be installed only when war was imminent, presenting an adversary that had assessed the vehicle's protection during peacetime exercises with an unpleasant surprise in the actual conflict that assessment was supposed to have prepared for. The vehicle's first public appearance in 1963 generated the kind of international attention that genuinely novel military technology rarely receives. American defense officials took notice, specifically of the combination of low height, relatively modest weight, and amphibious capability that the design achieved simultaneously, and which conventional tanks of comparable capability could not match. The American Defense Secretary at the time wrote a formal memorandum noting the advantages the Swedish design demonstrated over current American equipment in several specific respects. This was not a polite diplomatic gesture. It was a candid, professional assessment that the unusual vehicle had achieved something worth taking seriously. The subsequent formal evaluations conducted by foreign militaries confirmed and extended this initial reaction. Norwegian trials compared the vehicle directly against a contemporary German tank and found that, in the specific conditions of the evaluation, closed hatches, operational conditions rather than optimal demonstration circumstances, the turretless vehicle identified more targets and engaged them faster.
British evaluators spent 6 months with the vehicle and concluded that the turretless concept had genuine operational advantages rather than merely being an interesting experiment. American evaluators in the mid-1970s found that the vehicle's accuracy, when fired from prepared positions under the conditions it was designed to exploit, was competitive with American tanks, despite the mechanical difference in how the gun was aimed. The criticism that was consistently leveled at the design, that it could not fire effectively while moving, was technically accurate, but operationally less significant than the critics suggested. Swedish doctrine did not require the vehicle to fire while moving. Swedish doctrine required the vehicle to move to a position, fire from that position with maximum accuracy and rate of fire, and then move to another position before the enemy could respond effectively. The inability to fire on the move was a genuine limitation in tactics that required it. It was not a limitation in the tactics that the vehicle's designers had actually specified. The service history of the vehicle over 3 decades was, by any objective measure, a success. Reliability rates during exercises and deployments were high, unusually high for a design with as many novel technical elements as this one incorporated. The propulsion problems of the initial production batch, once resolved by the more powerful turbine replacement, did not recur as a chronic issue. The 3-man crew arrangement, unusual as it was, proved workable in practice and gave the vehicle a resilience that pure efficiency would not have provided. Any crew member could perform any function, which meant that battlefield casualties did not necessarily render the vehicle incapable of continued operation. The final evaluation, conducted in the late 1990s as the vehicle approached the end of its service life, had a quality of theatrical fittingness about it that would be implausible in fiction. 7 of the old turretless vehicles, by then approaching 30 years in service and representing a design conceived in the mid-1950s, were positioned defensively against 7 modern German tanks, a vehicle that had been evaluated in the early 1990s against every other main battle tank available, and had emerged as the top performer in NATO, widely regarded as the most capable tank in Western service at the time. The result was not close. The old vehicles, operating from prepared positions, using the tactics they had been designed for, hull-down concealment, rapid fire from the automatic loader, fast withdrawal using the rear driver, defeated all 7 modern opponents. They lost 1 vehicle in the process. The combination of low profile, high rate of fire, and tactical mobility that the turretless design provided in a defensive engagement in suitable terrain gave the older vehicle a decisive advantage over a technically superior opponent that was not optimized for exactly this scenario. The exercise result was not a vindication of the vehicle's design over all alternatives in all situations. It was a demonstration that the specific combination of characteristics the turretless design had developed for the specific environment it was designed to operate in remained effective even 30 years later, even against equipment that was superior by almost every conventional performance measure. The vehicle was not better than the German tank at everything. It was dramatically better than the German tank at the one thing that mattered in the terrain and tactical scenario the exercise had constructed. The retirement that followed was driven by factors that had nothing to do with the vehicle's performance in its designed role. The Cold War had ended. The Soviet threat that had justified Swedish defense expenditure had dissolved. Budget pressures made the development of a successor that could match the vehicle's tactical concept with modern sensor and electronics technology economically impractical. And the vehicle's armament, the 105mm gun that had been standard across NATO in the 1960s, had been superseded by a generation of larger, more powerful guns that the turretless hull could not accept without fundamental redesign. The electronics, the sensors, the fire control computer, all of it belonged to a generation of technology that had advanced beyond upgrade. Retirement came not because the concept had failed, but because the specific implementation of the concept
had reached the end of its useful technological life, and the political and economic circumstances that might have justified starting over with a new vehicle incorporating the same fundamental philosophy were absent. A small number of the vehicles were preserved rather than scrapped. They remain operational, maintained in running condition at a Swedish military museum, where they can be examined by anyone who wants to understand what an engineer with a statistical analysis and an unconventional conclusion was able to build when a small country decided his unconventional conclusion was worth testing. What those vehicles represent, beyond their specific mechanical interest, is an argument about how military technology develops and who gets to make the decisions that determine its direction. Berger was not a general. He was not a program manager with institutional authority over a major procurement. He was an engineer with a dataset, a conclusion that the dataset supported, and the persistence to keep making the argument until someone with authority decided the argument was worth testing. The testing took years and cost money, and required Sweden to accept risk that conventional procurement would have avoided. The results served the Swedish army for 3 decades, influenced the development of gas turbine propulsion in tanks that came much later in other countries, and demonstrated in its final exercise that the logic it had been built on, low profile, high rate of fire, tactical mobility, remained sound long after the specific vehicle that embodied that logic had become obsolete in other respects. The generals who laughed in 1956 were wrong. Not because the turretless tank was better than a conventional tank at everything, it was not.
They were wrong because they evaluated the concept against a universal standard rather than against the specific requirements of the specific problem the engineer was trying to solve. The question was not whether a turretless tank was better than a turreted tank in general. The question was whether a turretless tank was better than a turreted tank for the specific mission of defending Swedish terrain against the specific threat that Sweden faced. The data said yes. The vehicle said yes. The final exercise, 30 years later, said yes one last time before the vehicle went to the museum. Berger had been right. It just took a long time and a lot of people laughing before the evidence was complete enough to say so without qualification.